There we go. Does that look like what you expect?
Looks very good.
Okay, great. So thank you. And well, thanks the organizers for giving me a chance to present this work. I should say it's interesting to come after Professor Kurihara because I made my PhD in surface forces, although that was 20 years ago. So it was an interesting flashback. Okay, so I will talk about something totally different now. So this is a project that I've been doing together with Rainer Dahint in Heidelberg, who is not attending this meeting. Yes, so I'm sure that a number of people in the audience can testify to the benefits and advantages of neutron reflectometry, not just at the solid-liquid interface, which is what we will be dealing with, but despite all the greatness of reflectometry, there are some disadvantages. Among these, that there is no chemical information in these measurements, and it doesn't work well with thick layers, and it is relatively slow. These are well-known problems, and people have addressed these before. There are a number of references given on the slides, which you can look up. And particularly infrared spectroscopy together with neutron reflectometry has been implemented before. There was a beamline in Berlin, the BioRef beamline, which my collaborator Rainer Dahint was involved in. And also some attempts to do ellipsometry together with reflectometry before. We decided we want to do these three methods together. And well, it is popular these days to put different methods together to increase the amount of information, the types of data you get during the same measurement. And in this case, it is, I would say, fairly straightforward. So when we set out to do this, we had some requirements. We wanted the setup to be modular. So each of these methods should be possible to use independently of the others. And that is, well, the reason why this is fairly straightforward is that you can access the sample interface, the solid liquid interface, from different directions with each of these methods. So there is actually rather little physical interference. So in the figure, we have infrared light coming from one side, we have the ellipsometry probing from the other side, and there will be neutrons coming perpendicular to the image plane here. And the modularity is related to the flexibility. We wanted this to be a setup that could be used at different beamlines, so it should be relatively easy to rearrange. And we wanted this to be portable. We found that we were using experiments at different beamlines, and we did not really want to be stuck with one facility or one beamline for experiments, but rather have the flexibility to do this at different places. Right. So doing this, we went for the simple solution using available optical components, off-the-shelf components, because this will save time and it will surely save money also. So the ellipsometry part of this setup is well, it's called the in situ ellipsometer from John Woolam. It is actually a setup that is designed for being built into existing systems, just the way we want to do it. And it is fairly compact, very fast, and this is a relatively new system also, so it really comes with modern technology. The infrared part is currently sold with a stripped down benchtop spectrometer. So the Thermo Scientific IG50 is basically an OEM version of one of their top line benchtop systems, which it is not ideally suited for the purpose it will turn out, but we will address this later. But these are the bits and pieces that we put together with liquid cell and some optical interfacing to do experiments with these. Now, images of these types of systems are hopeless because they will be very cluttered, because there's a flurry of cables and pipes and tubings and all sorts of things. But here's an attempt to show what the setup looks like. So at the center, there is the trapezoidal prism, the silicon block, which is actually the sample. Beneath is a liquid flow cell, and this liquid flow cell has optical ports for the ellipsometric system. So in and out at about 60 degrees angle of incidence angle. And from above, we have infrared light probing in a 3 reflection setup on this trapezoidal prism, and it's exiting on the top side also. This whole system, the setup with the ellipsometry part is included. Well, there is the neutrons coming. We were looking pretty much down the beam direction. This is included in the infrared setup, where it's more or less confined between 2 big boxes, the source and interferometer box and the detector box. And looking at it from above, we have the part that I was showing in the previous picture in the center. As I said, it's a little bit difficult to show in a simple manner what it looks like, partly because it's confined and because there's a lot of stuff around it. But this was set up at Figaro. We had a setup at D17 also. So one is horizontal and one is a vertical reflectometer. So the setups will be slightly different, but that was part of the idea, that it should be flexible and possible to use at different beam lines. So we have tested this setup with different systems. So Rainer Dahindt has been working on a set of bilayer stacks, which I will not talk about today because of time issues. We have used a type of polymer system that we are interested in for anti-fouling purposes as a model system. So this is a copolymer, polyampholytic copolymer, or pseudo-citerionic copolymer from cationic and anionic monomers. The data I will show will not be from copolymerized system, but just the homopolymers. And the geometry of the sample is this. We have a silicon block, an oxide layer, silane layer to couple the polymer to the oxide, and then the polymer. And this will be measured in a lower high pH. And things we are interested in is like, what is the structure of the hydrated layer, the polymer layer, because the structure of the polymer layer will determine its anti-fouling properties. How fast does it relax? What is the speed of change, the rate of change if you change the environment? What is the degree of ionization in the film, for example? And these are questions that will be answered by different parts of this combined setup. So we've done fitting of the reflectometry data. We measured the cationic and anionic polymers in different contrasts, D2O, CM3, H2O, and also under dry conditions. So each sample was measured in 3 contrasts at low and high pH. The reflectometry model is fairly standard, I would say, for this type of systems. Now here, ideally, we would like to fit the neutron and ellipsometry parts together. But there is an inherent difficulty here, because we are using these 2 different methods because they are good and effective in different ranges, in different thickness ranges, basically. And this should really be taken into account. Well, basically the data should be weighed differently in different on different length scales. So this is a non-trivial problem which we haven't really solved yet. I'll show an example of what you can get from the fitting. So from the reflectometry data, we obtain volume fraction profiles under dry, stretched, and collapsed conditions. Here we use the thicknesses obtained from this fitting as input to the ellipsometry model, and then calculating the optical properties we obtain from the ellipsometry model with this data. And the optical properties, well, we are using a Cauchy layer with 2 parameters, where A is the refractive index, basically. And if we look at the A values that we get sensible A values for the polymer in some cases. These are under wet conditions, but not under dry conditions. And clearly,
2 more minutes.
Yes, thank you. If you look at the fits, you see that it doesn't really fit the data very well. So, well, to cut a long story short, we not yet know how to do this fitting, but this is something we're working on. We were doing infrared spectroscopy in parallel, and the data shows we can probe the bulk properties of the solution, so we can actually follow the contrast changes very accurately. For this particular system, we were interested in following the protonation and deprotonation, and this we can surely do. It's worth noting that the layers here are quite thin for an ATR experiment. So in view of this, I'm quite happy with the quality of the data we get. So there's some extra noise because we come near the silicon cutoff here. But otherwise, this is working fairly well. So to summarize, we tested this complete system on 2 different reflectometers, and it works well so far. So performance is meeting our expectations, but we are not happy, well, we're not resting. So we are still working to improve things. So there will be an upgrade of the infrared system, which will be on a separate slide to make it a little bit more flexible. We are adapting this setup for the ESS beamlines, and the intention is to have something that will be easy to use and useful for coming users. That includes also design for a sample changer, which probably will not be very easy to use with the infrared part, but certainly for the ellipsometry, I expect this to be working relatively well. And we are working on fitting the neutron and ellipsometry data. So the upgrade of the IRIS system is really a pressing issue to make this more easy to handle and make it more compact. So we will use a much smaller interferometer. There are a number of technical issues involved in the design here that I would be happy to talk with anyone who is interested, but it's not trivial to do this. But this will give us a much more compact and much more flexible system, and the whole setup can be pre-aligned, offline, and then just put into the neutron beam when you do the experiment. Yes, so that was it. I want to note that we've been working on this as a team with people from Linköping, Rainer de Hint and his 2 students from Heidelberg, and also Philip Gutfreund. This was funded by the Swedish Research Council. We got ample beam time from ILL through a long-term proposal, and adaptation for the ESS beamlines is supported from the ESS. And yes, thank you for paying attention.